Okay, so in a previous class, we had done a side-by-side comparison of the gravitational force and electrostatic force, and while they started off looking rather similar, by the end of the comparison we realized they're really not the same thing at all. The gravitational force is almost always completely much weaker than the electrostatic force. And so, why in the concepts were just reviewing gravitational force and field? Well, it's because even though there's plenty of dissimilarities between gravitational attractions and electrostatic attractions and repulsions, there are enough similarities, there are enough things that are similar, that we can use what we know about gravity to help inform understanding about electrostatic effects. And one of those things is field, right? We introduced the idea of the gravitational field because objects can attract each other at great distances. They don't need to be in contact with each other. They can be small distances also, but it doesn't matter. They're always sitting in each other's gravitational field, applying forces to each other without having contact necessary. And in physics, anytime that happens, we establish the idea of field. Well, you can see that clearly happens with electrostatic forces as well. In the demonstration you saw in the video with the balloons, they didn't have to be touching to repel each other. And so we have to establish the idea of an electric field again. Electric field as well, because it's the same general idea. So on the notes page, we're drawing some visual representations of field. We're going to start off here with an object of mass m. This is shown right on your notes page. You can draw these pictures right on that notes page. And what would this object do to other objects nearby? Well, it would always attract. And so how would we picture that? Well, we're going to show some arrows that are pointing radially inwards, and we'll label it with lowercase g. This is a visual representation of this object's gravitational field. What is this object? Maybe it's the Earth, maybe it's the Moon, maybe it's the Sun, maybe it's an atom, maybe it's you, right? All objects create their own gravitational field, and they always attract other masses, and so this is just a visual representation of that in 2 dimensions. It really happens in 3-dimensional space as well, but you can show that on the picture as well, very easily, right? And so what it does to space around it is any mass nearby will be attracted towards it. Well, charges create electric fields as well. So let's look at a positive point charge, positive Q. Alright, so what does this object do to other objects nearby? Well, we know the rules, right? It will attract negative charges and repel positive charges. The question is, which do we show? Because we certainly aren't going to draw arrows pointing both ways. That could be very, very confusing. So we have to choose one or the other, positive or negative. And whoever decided these things said, you know what, we're going to draw positive. And so we're going to always show what this source charge does to other positive charges nearby. And what does the positive charge do? Well, it's going to repel. Right? And so no matter what, we're going to field lines that point radially away. This is showing a visual representation of its electric field, which we're going to represent by capital E. That's our new symbol for electric field. Notice that I'm color coordinating here, and if you have colored pencils or ink, you can do so, but I'll always be using green for gravitational fields and red for electric fields. But on your paper, you better label lowercase g or capital E so you know which picture we're looking at. Okay, now there's certain rules that go along with electric field lines, and so in your notes we're going to start to list these rules for electric field lines. I want to have them all clustered together. There's going to be 5 of them in total, so just make sure you have room in your handwritten notes to write all 5. And the first rule is this one we just said, that no matter what, arrows always show the direction of the force on a positive test charge. What does that mean? Well, this test charge is the charge that's not creating the field. It's the one that's experiencing the field. So we have that source charge, that was that positive capital Q, that capital Q is going to be used for the source charge, and then we test for the field in the region of space surrounding it to see what would happen. And by convention, we always show what happens assuming the test charge is positive, right? And so in our picture here, a positive charge would always be repelled by the positive source charge. Now, in the end, it doesn't really matter what sort of charge we have. When we communicate with another person, or we draw a picture of the fields and show what's happening, we always assume the test charge is positive, even if in reality it's not. It doesn't matter. So our second situation here is, what if the source charge is negative? And so by our rule, we're always going to show what this source charge does to a positive test charge. And since the source charge is negative, it would always attract a positive test charge. So now all the field lines point radially inwards. Now, in reality, if we have a negative test charge, it would just feel a force in the opposite direction. So these electric field line pictures are like maps. They're maps of force, saying if you were to put a positive test charge here, what would happen to it? It would feel a force attracting it towards the negative charge. And so even if we don't know what the charge is creating the field, the map of the field tells us what sort of charge it is. Field lines point inwards towards a negative charge because a positive test charge would be attracted to it. Field lines point away from a positive source charge because a positive test charge would be repelled away from it. Now in reality, if we have a negative charge here, what would happen? It would just feel force opposite to the way the field is pointing. That's all there is, right? So the field is just showing a map of the forces felt by a positive test charge. Let's take a look at this situation. What if the source charge itself has double the amount of charge? Now, we haven't gotten to equations yet, but we should have the sense that this will have double the field strength of this charge. So how would you show that? In class, I would ask for suggestions, and often we get some really good suggestions, but there's one way that is the standard, and the way here is to show double the amount of lines. And so originally, if a positive charge had 8 lines here, and this is double the source charge, we're now going to draw 16. So you can fill in the gaps there with more and more field lines, now showing the field produced by a charge that is double the amount as this one over here. It's still pointing radially away because a positive test charge will always be repelled by the source charge. This brings us to rule number 2. The number of lines is proportional to the magnitude of the source charge. Now, it's always arbitrary how many field lines you draw when you start off drawing a picture of electric field lines. There's no way you could say this amount of charge has this amount of field lines, because the amount of source charges can vary by huge amounts, by orders of magnitude. You could have microcoulombs, and the next problem we could have nanocoulombs. That's a factor of 1,000 between. We're not going to draw 1,000 field lines. That's ridiculous. And so it's always arbitrary how many lines you draw. This rule comes into effect when you're comparing pictures. Or if you're in one problem and we have 2 charges or multiple charges, and you want to see how many relative field lines each one produces, how much relative field it produces, right? That's when you have the number of lines being proportional to the magnitude of the source charge. Let's take a look at this situation. Notice I've left you a lot of space on your notes page. We have 2-point charges, equal and opposite. So I've got the positive charge on the left, the negative charge on the right. This is what's known as the electric dipole. Okay, now immediately I want to make sure we understand what's happening. If I were to let these 2 charges go, what would they do to each other? Okay, so we know they would attract each other, and they'd try to pull each other in, and they would meet somewhere in the middle, but that's not what we're doing. In fact, the title of this whole unit is Electro Statics. And what does static mean? Static means stationary, not moving. And that means that the charges creating the fields, the source charges, for which I'm always using these capital Qs, are stationary. They're fixed in place. And so while, yes, they would want to attract each other, it doesn't matter. We're not going to let them, and they are attracting each other, but we're not going to let them go to do whatever they do. When we draw the field, we're always going to show what these objects do to our positive test charge. And so we're going to imagine a positive test charge in all different locations, here, or here, or here, or here, or here, and we're going to visualize what will these source charges do to our positive test charge. Now, we're not actually going to draw the positive test charge. In fact, if we've already drawn it, get rid of it. So we want to sort of imagine the positive test charge at different locations, but imagine you draw it as imaginary, right? So I'm not even going to draw it at all. I want you to draw it at all, but maybe if you need something physical here, maybe take your pen or pencil and put it right there in the middle between, and we're now going to see what these source charges do to our positive test charge. We're going to employ the principle known as superposition, meaning that each of these source charges will create its own field. We're going to show what it does to this one, and then we're going to superimpose them on top of each other, see what the net field is. And so we're going to play a game imagining one charge or the other. So imagine we only had the positive charge, and it's going to act on our positive test charge. Which way would our positive test charge feel a force from this one? Pause the video and think it through. All right, so hopefully you said to the right. Again, we're looking at what this charge would feel from this one. And this charge is positive, this charge is positive. This charge would be repelled away from this positive source charge. Now let's imagine we only had the negative source charge. Which way would our test charge feel a force? Pause the video. Hopefully you said to the right. Again, all we're doing is we're focusing on our imaginary positive test charge, and it would be attracted to our negative source charge. Now, they're both there, and both of those forces we just imagined are pointing to the right, so we can really just draw one single electric field line from the positive to the negative, pointing to the right. It's really just a whole bunch of arrows all pointing to the right, but they combine to form one net field pointing to the right. So a positive charge would be repelled by the positive, drawn in by the negative. All those fields combine to make one net field pointing to the right, anywhere in between. Let's now imagine our test charge is over here. And again, don't draw it. If you've already drawn it, get rid of it. You would never draw the test charge unless told otherwise. But we're going to play that same game. What if we only had the positive source charge? Which way would our test charge feel a force? Hopefully you said to the left. It's repelled away by our positive source charge. Now what if we only had the negative charge? Which way would our test charge feel a force? To the right. Remember, what we're doing is we're showing the overall field produced by both of them there together. So if this charge feels a force to the left from the positive and to the right from the negative, well, now they're not combining. Now they're taking away from each other. Or if we would add them as vectors, they would subtract. Do they cancel? Well, we should notice that our positive test charge is closer to the positive source charge. And while we haven't gone through the equations yet, proximity does win. And that should make sense. Anytime we deal with the gravitational field, right, the closer you were to the mass, the more of the field it felt. And so it's going to feel a stronger repulsion from the positive, a weaker attraction from the negative. Who wins? The positive charge wins. And so overall, it will be repelled in this situation. So the field points to the left, and draw a nice long field line extending all the way to the end of your page, because it just keeps going, right? A positive test charge closer to the positive charge will be repelled more than is attracted by the negative, and so this wins. And so the overall field points to the left. Remember, the field is like a map showing the force acting on the test charge. What if we imagine our positive test charge over here? We're going to play the same game. What if we only had the positive charge? Well, it would be repelled, so that force would point to the right. Remember, we're focusing on the test charge. What would it experience? It would feel a force to the right from our positive source charge. What if we only had the negative charge? It would be attracted. It would feel a force to the left. Who's going to win? Well, it's closer to the negative charge, and so overall this field would point to the left. We're superimposing the effects from both fields, from both source charges, but this one, this location is close to the negative charge, it wins, and so overall the field points to the left, and so draw a really long field line here with the arrow pointing to the left. Alright, this is a fun game, right? Let's make it more complicated. Let's imagine our test charges over here. Again, don't draw it. Just imagine it there. If you need to put your pencil cap there, or your pen cap, or your finger just on the page so you can visualize it, that's great. Again, we'll play the same game. What if we only had the positive source charge? Which way would our test charge feel a force? Well, it's going to be repelled, so it's going to be up and to the right. Now, don't draw this. Just imagine it. Watch the video, right? What if we only had the negative source charge? Which way would this charge feel a force? It would be attracted in. That's going to be down and to the right, right? Sort of like this picture and this picture, both here. Now, again, don't draw this, because both of them are there, and we don't want to draw the individual ones. We want to draw the overall field, and these are vectors. So now we have to think about this as a vector addition. Well, one way to do it is just look at this picture here, and you should be able to see that this vertical part here and this vertical part here are sort of going to cancel out. The upwards and the downwards are both equal, and they cancel out. Overall, then, they're both pointing to the right. Another way to think about it is by doing our usual tail-to-head method, right? We shift this vector over here, tail to head, and we draw the resultant from tail to head, and you can see the verticals cancel. And so overall, at this one location, we draw a tiny little arrow pointing to the right. It's only that location, because anywhere else it's going to be a little bit different, which we'll explore soon. Okay, what if we have our positive test charge here, right in the middle, but displaced vertically downwards? Let's play our usual game. From the positive source charge, it would feel a force away, down to the right. From our negative source charge, it feels a force towards, up and to the right. What's the overall field? Well, hopefully you recognize this is the exact same situation as when we had our test charge over here. The verticals cancel, both point to the right, or draw tail to head. And so at this location, with both those fields there, the field is pointing to the right. Push away from the positive, drawn in by the negative. Okay, this is a fun game, but let's now imagine, what if our positive test charge is here? Well, we're not going to go through the whole thing, but who's going to win? The positive, right? It's going to be repelled more than attracted by the negative. What if it's here? The negative is going to win. It's going to be attracted more than it's repelled. And so we could play a fun game, but in reality, it's going to be pushed away by the positive, drawn by the negative. We can draw one smooth, curved field line that passes through that point, indicating that anywhere along this field line, it would feel a force away from the positive, in towards the negative. So remember, this is like a map, showing if you put the test charge anywhere at this location, it's showing you the general direction of the force experienced by the test charge. What about down here? It would be repelled by the positive, drawn by the negative. We can draw a symmetrical field line, curved. Now, this is not showing the path of a charge. It's showing if you put a test charge here, it would feel a force along that field line. Feel a force along that field line. Of course, the negative charge would feel a force in the opposite direction. We can draw more of those field lines, sort of filling in the gaps. The farther you go, the farther spread apart the field lines are. Here would be a field line that goes away from the positive, and it gets so wide it leaves the plane of this field, leaves the picture, and comes back in over here. Here we'd have a similar looking field line pointing away from the positive, going way down, and we brought it here, and now we have the net field shown by the dipole. In class, I would ask you, what does this picture look like to you? I usually get some really good responses. Does anyone see a bug? Or maybe a beetle? Does anyone see a basketball? Maybe you see an onion. Maybe you see a bird with its mouth open. Whatever it is that's going to help you remember, this is the net field produced by the dipole.